M. Ludewig and G. Thiang's introduction of a uniformly localized Wannier basis in an arbitrary uniform discrete subset of a complete Riemannian manifold laid the foundation for understanding Wannier projections. Building on this work, researchers have focused on establishing the triviality of the class of a Wannier projection's orthogonal projection onto the span in the K-theory of the row algebras C, X, under certain geometric conditions. U. Kordyukov and V. Manuilov have provided crucial clarity on these conditions, demonstrating that they can guarantee the triviality of a Wannier projections class in K-theory. Furthermore, they have shown that triviality in a K-theory class is equivalent to triviality in a uniformly localized discrete unit. Manuilov has proven the triviality of Wannier projection units under uniform conditions within uniformly discrete local metric and geometric subset definitions. This involves considering continuous mathematical correlations among individual solution findings, achieving possible relative global mapping forms, and defining xd approximately equal y. These results have significant implications for understanding Wannier projections and their applications in uniform algebras. These findings highlight the importance of geometric conditions in determining the triviality of Wannier projections and provide a deeper understanding of the relationship between K-theory and uniformly localized discrete units. In a discrete space, the concept of a Wannier projection is intimately connected with the row algebra. Consider a proper metric measure space X with a uniformly discrete subspace D of bounded geometry. A Wannier basis for a subspace H phi of L2, X, is defined as a set of functions, phi x, x element of D, with non-overlapping supports and uniform bounded diameters. The Wannier projection P phi is then the orthogonal projection onto H phi. The authors also explore the construction of maps between row algebras from maps between spaces, following the method outlined in section 4. Specifically, they consider two metric measure spaces, X and Y, with respective actions of C0, X, and C0, Y, on their Hilbert spaces Hx and Hi. A coarse map F. X right pointing arrow Y induces a homomorphism between the row algebras C, X, Hx, right pointing arrow C, Y, Hi, where V, Hx right pointing arrow Hi is an isometry that covers F. Focusing on the case where Hx equals L2, X, circled times H and Hi equals L2, Y, circled times H for some Hilbert space H, the authors provide a detailed analysis of the row algebras C, X, Hx, and its properties. Notably, they show that the Wannier projection P phi exists as the image of the unit of C, D. This work builds upon previous studies on Wannier projections and their role in understanding the K-theory of the row algebra, with implications for the study of topological insulators and other physical systems. We examine the existence of non-periodic Wannier bases and their relation to topological obstructions, focusing on the definition of an isometry V from the space of continuous functions on X to a unidimensional subspace of H. This isometry induces maps X and ID in K-theory, which are independent of the choice of V and are isomorphisms when the measure on X has no atoms. Given a Wannier basis, phi x, X element of D, we define isometries U and A, covering the inclusion map D subset of X and inducing maps JC and JH in calgebras. These maps are organized into a commutative diagram of calgebras and their K0 groups. A key result, lemma 2, states that JC, 1, circled times 1H equals P phi circled times 1H equals JH, Q, where Q equals ID, 1, element of CH, D, following from the commutativity of the diagram. Theorem 3 establishes the equivalence of two conditions, P phi equals 0 in K0, CC, X, and ID, 1, equals 0 in K0, CH, D. This equivalence is shown using the isomorphisms, X, and JH, which follow from the coarse equivalence of D and X. Notably, the triviality of the K-theory class, P phi, of P phi depends solely on D, and not on X. This result has significant implications for the study of topological obstructions to the existence of non-periodic Wannier bases. A discrete metric space D is considered paradoxical if it can be decomposed into two subsets D plus and D, with partial translations f plus or minus laughing face right pointing arrow d plus or minus, which has implications on its K0 theory. Specifically, 1 is 0 in K0. C asterisk operator C, D, as per theorem 4.9 and 1. Alternatively, we can relax the isometry requirement on a family V of bounded linear maps from L2, D, to L2, X, by only requiring that V asterisk operator V is invertible. Using V's polar decomposition, we can show that T maps C asterisk operator C, D, to C asterisk operator C, X, while retaining properties similar to lemma 2 and theorem 3. A ray structure on D is defined as a collection of subsets, D, of D that allow for the formation of uniformly Lipschitz bijective maps from the set N, which is referred to as the ray. Deformation K0 theory yields a map gamma between commutative algebra and reduced group, linking geometric constraints and representations for ID asterisk operator 1. This enables the identification of structures that cause ID asterisk operator to become 0, facilitating description. Discrete uniformly bounded geometry spaces with ray structures can achieve 0 for ID asterisk operator P for the projection within K0. C asterisk operator C, D. The proof involves constructing a basis from H, which is simplified by restricting attention to di element of I that map uniformly through space. Isomorphic restrictions utilize sequences of operators along corresponding dimension representations or variations, providing geometric correspondences resulting from the theorem condition. This leads to functions applicable only at gamma over the projected case, thereby limiting operators and establishing that Th is non-existent, fulfilling the class being free of established elements. In topological insulators, the existence of non-periodic Wannier bases is influenced by topological obstructions. To investigate this, a graph D, alpha, is defined for alpha greater than 0, where vertices are points in a uniformly discrete metric space D, and two vertices are connected if their distance is less than or equal to alpha. A key theorem states that for a metric space D with bounded geometry, two conditions are equivalent. Firstly, there exists alpha greater than 0 such that the graph D, alpha, has no finite connected components. And secondly, there exists a discrete metric space D, with a ray structure and an isometric inclusion D subset of D, that is a coarse equivalence. The proof of this theorem involves multiple steps. When D, alpha, is a tree, either infinite without dead ends or finite, it can be decomposed into a union of rays, each coarsely equivalent to n for finite trees. They can be connected to a ray from another tree and then proceed similarly. This decomposition can be extended to the general case, where D, alpha, may consist of multiple trees. However, shared edges between trees require cloning to create a decomposition into rays, resulting in a new graph D, that is coarsely equivalent to D. Conversely, assuming the existence of D, but not condition 1, implies that for any alpha greater than 0, there exists a finite component of D, alpha. This leads to a contradiction, as the diameter of the finite component is bounded by C alpha, whereas the diameter of D, alpha, is unbounded, thus proving the theorem. This result has significant implications for understanding topological insulators and the role of topological obstructions in non-periodic Wannier bases. Uniformly discrete spaces of bounded geometry exhibit unique properties, particularly in regards to their coarse invariance and Borel-Moore homology. A key theorem states that if a uniformly discrete space D has finite components for any alpha greater than 0, then its coarse invariant, ID 1, is 0 in K0, ch D. This result is achieved by constructing a uniformly discrete subspace D, of D, which satisfies specific conditions related to coarse geometry. A corollary to this theorem elaborates on the connection between the coarse invariant and Borel-Moore homology, asserting that ID 1 being 0 in K0, ch D is equivalent to the Borel-Moore homology class C being 0 in the direct limit of HBM0 D alpha. This equivalence provides a new perspective on the coarse geometry of uniformly discrete spaces, bridging it to algebraic topology. The paper also explores the possibility of finding a more direct proof for this equivalence, avoiding graph theory. Such a proof would simplify the understanding and application of these results in future research. Overall, this work contributes to the ongoing exploration of the interplay between coarse geometry, Borel-Moore homology, and algebraic K-theory, opening up new avenues for researchers to delve deeper into the intricate relationships between these areas of mathematics. In a connected proper measure space X with bounded geometry, topological obstructions to the existence of non-periodic Wannier bases are examined. A key lemma establishes that if two uniformly discrete subsets, D1 and D2, are coarsely equivalent to X, and D1 fails to satisfy property 1 of theorem 6, then D2 also fails to satisfy this property. This lemma is instrumental in proving corollary 11, which states that for any Wannier projection P phi with a uniformly discrete set D of localization centers coarsely equivalent to X, the class P phi is trivial, i.e., P phi equals 0. The proof of corollary 11 involves constructing a uniformly discrete set D of bounded geometry that is coarsely equivalent to X. This is achieved through the application of Zorn's lemma, which enables the identification of a maximal discrete RDIS joint subset D in X. The set D is demonstrated to be uniformly discrete and coarsely equivalent to X, with bounded geometry. Moreover, the graph D, 3R, is proven to be connected, thereby satisfying property 1 of theorem 6. The existence of such a set D has significant implications for the study of Wannier bases in X. Specifically, the triviality of P phi implies that any Wannier projection P phi with a uniformly discrete set D of localization centers coarsely equivalent to X cannot be used to construct a non-periodic Wannier basis. This result highlights the importance of considering topological obstructions when investigating the existence of non-periodic Wannier bases in connected proper measure spaces with bounded geometry. The relationship between geometric complexity and topological rigidity in noncompact manifolds is explored through the introduction of a novel notion of geometric complexity. This concept is defined as the minimum number of topological generators required to generate the fundamental group of a manifold. By applying this concept, a coarse Mayer-Vietoris principle is established, providing a new perspective on the study of topological rigidity. The theory of Wannier bases is leveraged to investigate the implications of large-scale geometry on localization in non-periodic insulators. The presence of large-scale geometry is shown to obstruct localization, leading to significant implications for the study of topological insulators. Furthermore, the connection between the localization of generalized Wannier bases and Chern triviality in non-periodic insulators is examined. The localization of such bases is found to imply Chern triviality, highlighting the intricate relationship between geometric and topological properties of insulators. The interplay between geometric and topological properties is crucial in understanding the behavior of non-periodic insulators. The findings of this research have significant implications for future studies in geometric complexity, topological rigidity, and non-periodic insulators. The importance of understanding this interplay extends to various contexts, including infinite graphs and coarse geometry. The research highlights the need for further investigation into the relationships between geometric and topological properties in these contexts.